Okay. Next topic area we're looking at, acoustic emission. And we'll note one thing you'll notice when we get into acoustic emission is very similar to ultrasound. So it's going to have a lot of similar kind of terminology, similar equipment to what we use during ultrasonic testing. It is a little bit newer application, although when I say newer, we're talking about things like, I'm comparing it in relative terms. So, things like X-ray has been around since the 1940s, 50s, right? Things like mag particle have been around since the same time period. A lot of stuff was developed in the World War II, post-World War II era. Acoustic emission really came about in kind of the probably early research 1980s, and then development in the 1990s, and it's becoming, with computers and miniaturization of electronics, and electronics becoming, less expensive by, not just dropping in price slightly, but like over the years have become so cheap that you can, or so inexpensive that they can be installed with minimal cost increase, particularly when we look at it relative to the cost of aviation. And so these systems have been developed, and most of them are going to be what's called in situ or in situation. They're permanently installed where they are, and they're able to monitor all the time, or able to be turned on when monitoring is necessary. So looking at what is acoustic emission, the dictionary definition, using dictionary words, the generation of transient elastic waves produced by a sudden redistribution of stress in a material. And to make it simpler, external stimulus, such as a change in pressure, load, or temperature, is going to cause the release of energy in a part in the form of stress waves. And these can then be recorded by a sensor. And just like ultrasonic, they tend to be, most of them are in the ultrasonic range, and they're going to be detected by a piezoelectric detector. Piezoelectric detectors, piezoelectric receivers can be made incredibly cheaply, incredibly inexpensively, and so they're very similar to those ultrasonic transducers. So here's a quick video on what acoustic emission is, and then we'll discuss it in detail. So acoustic emission has some fairly strong advantages. The biggest one is it's very material interdependent. It can be used on all kinds of things. So, you saw just in that short video that was applied to things made out of metal. It can be done on your fiber reinforced polymer matrix composites. It's a fancy name for fiberglasses, carbon fibers, and those kind of things. Also things like concrete and wood. And so these are used often in the civil engineering and in the in the transportation sectors for things like structural health monitoring of things like bridges and buildings. And so it's very versatile in that regard. It can be set up in a way, it's incredibly fast, and it can actually be continuous. Again, with this stuff installed permanently, you can have a monitoring system that runs 24/7 and is able to look for, the initial kind of, if all of a sudden we start to have some kind of a acoustic signal being generated, to be an early warning sign or a red flag. And so it can provide, with computers, data acquisition and analysis. Most of the time, I say very often performed on objects in use, but far and away more often on objects in use than as a standalone technique like we've done with pretty much everything else. And then it can be automated, is a big part of that. The data acquisition analysis can all be done in a computer. Most of the analysis that's going to take place with it is going to be algorithmic based anyways. It's very hard for a human to look at a waveform and really tell exactly what's going on. And so you need, things like different algorithmic, and now obviously we have AI and learning models and that kind of thing that can perform this without or with minimal human interaction. Because these can be permanently installed. They can be put in places that we may not be able to access once an object is fully constructed. There are sensors that can actually be included in like a composite layup between layers, or as part of the structure. They can be installed in areas that, during assembly, once they're put together, you're not going to be able to access. For permanent, they can also be removable. They can be installed and removed. Like I was saying, in the factory environment, we had a portable acoustic emission device that was basically it had like a long rod type probe, and you would touch it to different objects. You'd touch it to motor frames, you'd touch it to bearing housings, you'd touch it to different pieces of machinery, and it would be able to capture an acoustic, that acoustic signal based on the vibrations that were transmitted into the little probe. And minimal preparation. You typically, if it's installed in permanent, there's really preparation. It's part of the installation or build process. But again, even like in that portable environment, the factory environment, for instance, it's very dirty. We had oil, grease, and graphite everywhere. But when you touch the probe, you kind of just clean a little area and touch the probe to it. You really didn't have to like clean the whole press or clean the whole production line. You could just kind of touch it to it. I know that sounds bad. People want to think of factories as like clean and all that, but most of them are not. It's very hard to keep things clean in like a steel forging or casting plant. It does have some disadvantages though. So the first one is that it is a dynamic process. So the material has to be actively changing or stressed in some way for this to work. It can't just be sitting there. The flaws have to be a type that are going to produce an acoustic event. So there are flaw types that don't necessarily produce acoustic events, produce an ultrasonic signal. And so those ones won't be able to be picked up by acoustic emission. Currently, for the most part, although less and less because of research, it's qualitative only. So early on it was, did a flaw occur? But it was very difficult to figure out exactly where it occurred. Now we've gotten a lot better at being able to find location. We'll talk about location determination further on in the lecture. But what is particularly difficult to figure out oftentimes is what is the amount of damage that occurred? How deep is the crack? How wide is the crack? If you have odd geometry, it can sometimes be hard to figure out exactly where, in a complex geometry part something had occurred. But again, there's a lot of research that's going into this and development, and particularly with, again, things like algorithm development, analysis development, that are helping to improve that, and it's getting better every day, where it's becoming more and more useful. One thing that you do have to be aware of is it can be sensitive to extraneous noise. Now, the nice part is a lot of the ranges that this is operating in, we don't have a ton of extraneous noise. Okay, it's up in those ultrasonic ranges, and in most cases, you don't have a ton of noise, right? Most of your vibrations, so you have a motor, a motor running at 3,000 RPM. Well, that actual just rotation is not going to produce really anything in that kilohertz, like tens or hundreds of kilohertz or megahertz range. Most of the vibration is going to be in the 3,000 hertz range. But there are cases where that could be a problem. If you do have extraneous noise, you have to be aware of that and not have it be like a false positive, a false indication, or you might need to filter out certain ranges. So that theory, that definition, right, the acoustic emissions, the result of the initiation or growth, things that we can find are things like cracks, slips, dislocations. Those are all, so cracks and slips we've seen. So a slip is kind of like a shear type plane. Twinning is like the twisting or bending of a material. It's often a torsional, a result of a torsional force. Okay. And then phase transformation, things like freezing and thawing, you can actually hear, right? Many of you have probably, who's been out like on a lake when it's freezing and had it crack on you? Have you ever been on the lake like ice fishing and had to do that? And it scares the heck out of you. You're like, what's about to happen? Am I going to go under, right? So, that is a form of acoustic emission that occurs because of a phase change. That water turning into ice expands. Well, at the same time, if that water is inside of, say, a steel vessel and it expands and it causes the steel vessel to crack, that's probably going to give off some kind of an acoustic emission, right? So phase change as well as cracks and that kind of thing can be picked up by them. Those produce those stresses, application or removal. It can also be something that's been under stress and you remove the stress. They're going to create those elastic waves. They're going to create a sound wave that moves through the part. And we're going to detect that and analyze it to try to figure out what in the world is happening. When I worked at a ski shop, one of the most fun things we would do is when we got skis. Skis are big composites, fiberglass, all that. We take the ski, you hold the tip, you hold the middle, and you flex the crap out of it, almost bending them into a C shape. Brand new skis, and people would be like, what in the world are you guys doing? Well, when you did that, the first time you did it, there'd be all kinds of built-in stresses from the manufacturing, and they would crackle like popcorn. Anyone know why we did that to all the skis before we put them on the wall? So when a customer came in and started flexing it because they thought that was a great way to test a ski, it wouldn't sit there and crackle and make them think there was something wrong with it. Every brand new ski would do that because there are certain stresses that are in the manufacturing. So when you have particularly new things like new layups, a new, say, composite spar, there will be a certain amount of normal acoustic emission that takes place during the break-in period, okay? So when we're performing acoustic emission, we're going to be looking for something, a specific item called a waveform. And a waveform is a single useful signal. And these are typically transient or a burst signal. That means they occur for a short period of time when the damage actually occurs, right? We don't want to necessarily look at long-term, although things like motor monitoring and that kind of thing, you're going to listen to kind of the general sound, bearing monitoring. But for particularly in aviation, where we're looking for things like damage, it can also be used for impact damage, like bird strikes and other stuff. We're looking for that sound that occurs right at the moment of stress or right at the moment the stress is relieved. And so we're gonna get that burst signal, that transient signal, and we're gonna analyze several elements of it. So the first is the amplitude of the signal. And the amplitude is the greatest measured, say, voltage. Remember, this is we're looking at this from an electrical standpoint because we're taking that sound signal and we're sensing it using a piezoelectric receiver. And that piezoelectric receiver, right, puts out an electrical signal, puts out a voltage change that corresponds directly to the physical vibration that is hitting that piezoelectric crystal. And so looking at it from kind of an electrical standpoint, the amplitude is the greatest voltage that occurs in the waveform, and that directly corresponds to the strength of the sound or the decibels. Okay, so it's looking at voltage, but it correlates with decibels of the sound. The threshold is, remember, there's always some background noise and all that, so we're going to set a point where, like, okay, anytime the amplitude is below this threshold here, we're not really too worried about it. Right? We're primarily going to look at it when it exceeds a given threshold. And that has to be defined by, it's a combination of material science and, other experts in the field to figure out what is that amplitude? What constitutes a waveform? What constitutes a signal versus just the normal noise you would expect out of a given object? And so that sets our threshold. The rise time is how long that signal strength is increasing. So from the first time it exceeds the threshold to the time it reaches its peak, that's known as the rise time. Okay, some signals could be a very quick crack type rise time. Some are a little bit slower, especially if it's more of those twinning, like a slipping or something like that where it's twisting, right? It may not be an instant crack. It may have a little bit of a rise period. We're still talking fractions of a second here, but is it 1 or 2, fractions of a second, thousandths or millionths of a second, or is it 20 or 100 million, milliseconds? What is it? So that's our rise time. The duration, how long does our signal remain above that threshold that we've defined? So here's our duration shown at the bottom from the first peak above to the last peak above the threshold. Counts essentially how many cycles of the wave, number of signal amplitude peaks exceed the threshold. Okay. So counts, and they're shown down here, you can see. So count 1 is this peak, count 2 is this peak, count 3, and we're counting the peaks above. You also have, the inverse side of it, right? The peaks below, but you count each cycle, one period of the wave. And then, so those are all terms that you're probably somewhat familiar with, or like count seems pretty intuitive. The term that most people probably don't know is Mars, and that is the amount of energy that is released, or the amount of energy that's detected. And that is the area under the curve. Especially we take the absolute value of the threshold, or of the signal, right? And see this line that's been kind of created here, and that gives us the area underneath, the area contained inside the sound wave there. And so that is, it gives us the energy released. Okay, so here's just a little bit bigger. Again, that Mars is this area above the threshold contained underneath kind of that line we've drawn over all the peaks. So the theory of acoustic emission starts to rely on the signal that we're going to get, the intensity, the amount of energy we're able to detect, is going to be directly related to how far the sensor is from the source. What is that proximity, right? And that makes sense because we know when we talked about ultrasound that sound traveling through a material is going to be attenuated. Its total energy is going to be reduced the further it travels through material, the longer the distance it is, just because of the resistance of the material to the transmission of sound. And so when the signal is, that's the damping part. I kind of got ahead of myself. So damping is going to reduce the signal. The other part of that is a signal is going to travel in 2 dimensions or 3 dimensions, right? And so right where the signal is released, there's a certain amount of energy, and then that's going to spread through the part. And so you have that same amount of energy being spread over a bigger area, or throughout a larger and larger volume. So in a given location, as you get further and further away, the amount of energy that a sensor is going to pick up is going to be reduced. And it's going to be reduced exponentially. If you're talking in a 2-dimensional plane, it's going to be reduced by a square, or an inverse square. Or if it's in a 3-dimensional object, it's going to reduce over distance by a cube, or an inverse cube, right? 1 over the cube of the distance. Because that amount of energy is being spread through that area or that volume. And so what we get is kind of these general rules. So geometric spreading signal is spread over a greater area or volume. So for each doubling of distance on a plane, you lose roughly 30% of the amplitude. And for each doubling of a distance in a 3D structure, you lose roughly 50% of your amplitude. And so that has to be taken into account. It can also be used, we'll talk about multiple sensors to help pinpoint locations and things like that. The third element of reduction, so we've got spreading, damping, which is the attenuation due to the resistance, and then wave scattering if we have a part that's non-homogeneous, that has acoustic barriers in it, or acoustic interfaces, right? Vocab words from earlier sections, right? Acoustic interface. What's an acoustic interface? You're failing me right now. You're all going to just fail the final. Someone can't answer this. Acoustic interface. What is it? What's an interface? What's an interface? Nothing? Joining between 2 things. So where you have 2 different materials, sound, right, it's where we put the probe on the part. We have to couple it using gel, right? Otherwise, the sound doesn't transfer very well because we have an acoustic interface, a poor acoustic interface or a barrier. So if you have a material that's non-homogeneous, What's a non-homogeneous material? You can give me an example. You don't have to like define it. What's the non-homogeneous material that you guys and gals have all worked with extensively? Well, somewhat. What's that? Oh, aluminum's homogeneous. It's pretty much the same material all the way throughout. Carbon fibers are fiberglass, right? You've got the plastic, the epoxy that forms the plastic, and then you've got fibers embedded in there. Well, everywhere it goes from plastic to fiber, back to plastic to fiber, back to plastic, right? Each of those is an acoustic interface. So that tends to attenuate the sound and scatter the waves more than something like a pure metal where it's homogeneous throughout, where it's the same material as you travel through it. Okay. It can also be rough or uneven surfaces, like remember when we did sound, most of you have done ultrasound, and what happens when you move the probe over the corrosion area? The amount of energy and the signal drops because sound's getting scattered all over the place. Okay. So those are attenuation mechanisms. The other thing then I mentioned was noise, and we have to keep into account that there could be undesirable signals that we could pick up, and we want to make sure that we don't mistake those, or that they don't, you don't want to mistake them for a flaw, or you also, even more importantly, you don't want them to mask a flaw, right? And so things like friction from things like loose bolts, wind, expansion and contraction points, flex, those are all normal. We can also have impact, right? If it's raining out, rain can be very loud. Anyone been in an airplane in heavy rain? It gets very loud up near the front. You can hear the rain hitting the leading edge and the nose. And then mechanical vibration and noise, other components, engine components. There are things on some of our airplanes, right? An APU, a lot of APUs turn somewhere between 50 and 60,000 RPM. That's getting into the ultrasonic range. So just the spinning of the APU is fast enough to create ultrasonic sounds. Even your large engines are spinning at 10, sometimes 15,000 RPM. Right? Turbo, if you have a turbocharger, some turbochargers can spin close to 100,000 RPM. So just to give it 60,000 RPM is 1,000 rotations per second. That gives you some idea of how fast these are turning. Hard to kind of wrap your head around it. Negating noise effects, so we can use things like electronic gates and filters. We can also do physical distance. If we can put our probe in multiple places, we don't put the probe right next to the APU. We put the probe somewhere where it's further away. And then different filtering. We can also look at like arrival time or spectral content. If we know what the APU sounds like, or what the APU signal is, we can filter that out. We can look for that and say, no, we're going to ignore that, right? That high frequency or turbocharger. So the equipment should look fairly similar at this point because it's actually very, very similar to ultrasonic testing equipment, minus the fact that usually we aren't generating the sound. We're not generating the sound wave. We're just looking at the receiver side of it, okay? And so we have our sensors and then some kind of signal and capture detection equipment, which usually involves amplifiers and preamplifiers, potentially filters. And then we're going to perform analysis on it. The simplest form is like an oscilloscope that provides a waveform, or even like a little voltmeter. But if you just see a little arrow swinging around or pointer swinging around, sometimes it can be kind of hard to tell what's going on. That sound may be getting more intense or less intense, but that's about it, or you might be able to tell the frequency's gone up or down. But then you're going to have a detection instrument, and it's going to give you those sounds. And so I've got this is just a little animation. Nothing too fancy, but see, there we go. We've got a crack forming, and our acoustic sensor there is going to pick it up, and it's going to provide some kind of a readout for what's happening, for the sound that's being generated. So, well, and they're showing the beam, under load. We have to stress the object somehow. Looking at it a little bit more, here's, just kind of, again, that setup, our sensor with a preamplifier, our instrument, and that instrument can be put out to, different kind of visual representations of digital displays, or can go into, some kind of a computer analysis system here, typically both. The sensors are very similar to your ultrasonic sensors. Again, this actually is an ultrasonic sensor, but they're the same thing. You have a piezoelectric crystal or element with you know, some kind of a bonding plate. Now these, instead of couplant, they're going to be typically bonded right to the surface if they're permanently installed. There are special epoxies you can use to do this. And then there's going to be a damping material behind it to prevent extraneous signal from coming in from behind. It also helps to concentrate the signal on that piezo element to amplify what's happening in there. Okay. And then the signal is often going to be pre-amplified and filtered. And that is almost always the pre-amplifier is we need to get something, right? This is a very, very small voltage change. We need to be able to get something from the sensors over to what we're going to use to measure it. So this is kind of a little same image, just a little bit more accurate of what's going on. So the transducers often have an integral preamplifier in them to boost the signal, to send it, you know, say out from the wingtip back to the computer that's in the avionics bay somewhere, you know, something like that. Or from all over the bridge to get back to a box that's, you know, tucked under a bridge somewhere with a, you know, to do this. And so they're placed on the transducer. They're going to boost whatever signal's coming in. And so oftentimes they may have filters included with them as well. So then they're boosting just the signal we're interested in and filtering out any extraneous noise. But then they're still going to be limited in how much they can boost the signal. And so often in the analysis equipment and measurement equipment, there's probably another amplifier, may have additional filters in it that boost the signal to a point where it's usable. And so filters can be different types. Often we'll have, the most common we'll probably have is like a low pass filter. Sorry, a high pass filter, excuse me, because we're looking at ultrasonic signals. We get rid of anything below our area of interest. If there are high frequencies present above what it is we're looking for, we may have a low pass filter, which eliminates frequencies above us at that point. And probably what's most common is a combination of the two known as a band pass filter. And so we get rid of everything below and above, you know, a set range that we're interested in, a target range. And so the big thing here, difference, a preamplifier tends to boost a less, you know, we boost the, preamplifiers tend to boost the raw signal, then we filter it, whereas a main amplifier is going to boost that filtered signal and it may filter it further. You know, you may have additional filters further in the clean signal. Okay. And these are almost never used by themselves, but rather you're going to have an array or multiple sensors all tied into the same system that's shown here. So vibration sensors feeding into a single acoustic emission system. And again, that most basic form, voltmeters or oscilloscopes, but most are computer-based nowadays. And these can be portable. They can be tied to a standard laptop with software and interface, or they can be a fixed specialized device like we would have in aircraft, a card or a computer down in the avionics bay that interfaces with the sensors in order to provide data analysis and capture. And the fixed ones, the ones that are installed, provide that real-time continuous data that can be so helpful for things like spar condition monitoring as the wings flex, or impact, you know, from bird strikes or other stuff like that. When we perform this, one of the important parts is we need to figure out where that source was. Where did the sound originate from? And so, as I talked about with different materials, homogeneous materials are going to be much easier, where the sound transmits fairly evenly throughout the material, as opposed to materials that are odd shapes or that are non-homogeneous, have a lot of different internal structure. We said things like metal beams and metal aircraft parts, those are fairly homogeneous. Things like concrete, right? Most concrete is steel reinforced with rebar. That's non-homogeneous. You're going to have acoustic interfaces at each area where it goes from steel or concrete to steel back to concrete on the other side. And then like our composites, our carbon fibers, our fiberglasses, you're going to have lots of transitions between the plastic, the polymer material, which is your epoxy, and the fibers, whatever type of fiber they may be. The shapes can also affect it, right? Sound's going to move through complex shapes in a complex manner. And so that has a direct effect on how we're able to determine source locations. And then there's three kind of primary ways that we can look at our methods. We can look for linear location, what's called zonal location, or the most sophisticated systems are going to find point locations. And that is, that are kind of what we're going to have here. So if we're looking for, you know what? I want to do this all at once. So we're going to stop there and we will pick this up next time.